MacMaths, MacMaths. Let's do some maths today. Welcome to part C. Part C. I've ticked it for you. Harder examples of pulley questions. Okay, let's move that out of the way. And this is the example that I used in part B of these two blocks. Of 4 kilograms, you may remember, and 2 kilograms hung over a pulley, and we worked out the tension and the acceleration. And we worked out that the tension was 26.1 newtons, and the acceleration turned out to be 3.27. So if you can't remember why that is, you need to look at watch part B, because I go through that. That's when we split them into two halves. So you always have to do that when you're doing a pulley question. Now then, moving on. So they make them harder than this. So sometimes you get harder ones, and they combine it with equations, equations of motion. That's your SUVAT equations. So they may go on and do this. This is what I'm going to show you now is very typical of Edexcel. I've seen this type of question on lots and lots of papers. Nearly all of the old M1 papers would have something like this. It was a real favourite. The one I'm going to show you then is this. So I'm going to say you've done all this. This would be part A and B and C of the question, working out the tension and the acceleration. We've done that in our previous lesson. So now what they say is that it's released from rest, but they were at rest 2 meters above the floor. So what's going to happen is when we release it from rest, that this is going to fall down 2 meters and stop, and that's going to go up 2 meters. Okay, and the question that I'm going to ask you is, and this is how you would get it, it would say released from rest, and you would get what, and this is a very common question, what is the greatest height A reaches above the ground? There's a question for you. Okay, so what is the greatest height A reaches above the ground? So that's what we're going to do now. So I want you to think about this. I want you to think about somebody on a bridge doing a bungee jump. Okay, and when they jump over like that with the bungee, there they are, upside down. When they jump off the bridge with the bungee loose, they start to fall, don't they? And eventually they reach the point where the bungee becomes taut. Oops, becomes tight, doesn't it? Okay, and because they've reached up an acceleration and a speed, they keep going down, and they stretch that bungee like that, until the force in the bungee is so stretched that it resists any more downward motion and catapults the person back up. Now the person starts to accelerate up, and at the point where the bungee goes loose again, so in other words reaches its original length without being stretched, the person doesn't just stop dead, do they? What they do is they carry on then slowing down with that bungee getting looser and looser. Okay, so they carry on slowing down, and just under gravity, and then they come down and they bounce up and down, like that, don't they? Okay, so this is what happens here. So what I'm trying to say is that when this is released from rest, this travels down 2 meters, the heavier one. A travels up 2 meters. When this hits the floor, of course B stops. And what happens to the string then is the string becomes loose. But A doesn't stop moving up because it's reached a velocity. Okay, if I was to push this up and just stop my hand, it would carry on going a little bit further, wouldn't it? And that's what happens. So A accelerates up. The moment the string becomes, as B hits the floor, the string becomes loose. It carries on and slows down under gravity. And we want to find, how high it reaches above that point. Okay. So, first of all, some assumptions. we've got to assume, obviously, for this to work, that the pulley isn't going to get in the way. So this distance here is a lot more than the 2 meters, so it's never going to reach the pulley. So they usually say that. Okay, and the first thing that we know is that so we're trying to work out how high A reaches above the ground. So once this is released, it's going to get to this situation and it's going to become this situation. Okay, so I'm going to draw it here now. Okay, so B hits the floor, there's B, and this comes up over there, there's the pulley, and we're up to there. Okay, so 4 kilograms hits the floor and 2's gone up. Now at that point, that now, of course, is 4 meters, isn't it? Okay, because that's gone down 2 meters and A has gone up 2 meters. Okay, but this has got velocity. Now what we want to find now is how much further A travels. So it keeps going up, doesn't it? And we want to find out how much further it travels. And when we find out how much further it travels, we know that's how far it is above the ground. Okay. How much more it travels, of course, is that equations of motion. You know, it's the the up and down, the projectiles that we did going straight up. We need that initial velocity. Okay, we know that the acceleration once the string goes loose is not the tension anymore. The acceleration is going to be gravity, which is minus 9.8 meters per second to the minus 2. So we just need to work out that initial velocity. Okay, so let's do that then. First of all, okay, it starts to accelerate. If we use v squared is equal to u squared plus 2as, okay, and we're trying to find the velocity once it's reached this point here. Okay, it was originally here, 2 meters above the floor, but it's traveled another 2 meters, but all the time it's been accelerating up by 3.27 meters per second. So the new velocity after the initial velocity was 0 because it started from rest, plus 2 times the acceleration has been 3.27, and it's been travelling for, of course, 2 meters. Okay, so the velocity squared is, if we work that out, I'll work that out. It becomes, when we square root it, becomes blah blah, and when we square root it, we get 3.6 meters per second to the minus 1. So this hits the ground at 3. Speeds up from 0 to 3.6 meters per second, and this one speeds up and reaches 3.6 meters per second after it's travelled up for 2 meters. At that point, the string is now loose. Okay, so the string is not pulling it up anymore. So that tension has just gone, and now it's on its own. Okay, it's got a speed. Okay, and it's going to slow down to 0, isn't it? And then turn and fall back down again. But we want to know how far it reaches. That's the highest point above the ground. Well, that speed that it reached now becomes the starting velocity in our next stage. So now we can put that in as our u in our next stage, and we want to know how high it travels. Okay, now if we wanted the time, we would use v equals u plus at, but because we want the height it travels, we're going to use the same equation. We're going to use v squared is equal to u squared plus 2as again. Okay, so this was for the first stage, travelling the 2 meters, and this is for the second stage. Okay, so we're going to use v squared equals u squared plus 2as again. Okay, and the velocity at this point, at the highest point, is 0, isn't it? So 0 squared is 0. The initial velocity is the velocity it reached here. So this velocity is going to be our 3.6 squared plus 2 times, now the acceleration, of course, is gravity, and gravity, it works the other way. It's slowing it down, it's decelerating it at minus 9.8 meters per second squared times s. Okay, simplifying this, 2 times minus 9.8 is minus 19.6 s. Take that over to the other side. 19.6 s is equal to 3.6 squared, and if we divide 3.6 squared by 19.s, we will get 0.66 meters. Okay, so 3.6 squared in your calculators, divide by 19.6 gives us s. Alright, so that means that A, while this travels down 2 meters, A travels up 2 meters. So then it is 4 meters above the ground. It then slows down from a speed that it reached of 3.6 meters per second to 0. That's its highest point, and it travelled another 66 centimeters, 0.66 meters. That's 66 centimeters more. So the highest point A reaches above the ground is 4.66 meters. The original 2 meters, the 2 meters it travelled getting pulled up, and the 66 centimeters it slowed down to 0. At that point, at 4.66, of course, okay, it starts to fall back down to earth, doesn't it? Okay, until the string goes tight again. All right, now I have got a question for you, so I want you to have a go at that. It's about as hard as it can get, really, at A level, even at A2 this. So I hope that sort of made sense. I know it's not the easiest of things to get your head around, okay, but I want you to put it on pause, okay, and have a go at that question. So read the question, 2 blocks, A and B, masses 3 and 5, so you'll have to work out the tension and the acceleration again. We don't need the tension, but it's just you get it as a byproduct. They're held 3 meters above the ground. This time the system is released from rest for 1.5 seconds. The string breaks, oh no, favour it again with Excel. From this point, how long does it take block A to reach the ground? Okay, so have a go at that. Put it on pause, have a go. Okay, right, well, I hope you've had a go at that. And now I'm going to go through that question with you. The first thing I'm going to do is going to do what I said we do with all mechanics pulley questions, and that is, okay, well, we always draw a diagram, 2 blocks A and B, 3 and 5, A and B, okay, and we need the tension and the acceleration, so we always split them up into 2 and have an A side and a B side. So A and B. Okay, so let's put the forces on. Tension, acting away. Mg. Okay, so all the forces are on now. This one is coming down, so F equals ma. 5g minus t is the net force, isn't it? It's going down, so if that's the leading force, take away whatever that is equal to the mass times the acceleration, is equal to 5a. And on this side, F equals ma. That's accelerating up, that's accelerating down. So F equals ma for this side here, and we've got t minus 3g is equal to the mass, which is 3 times a. We combine those two. Okay, so if I go t is equal to 3a plus 3g and put it into here, I've now got 5g minus all of this, 3a plus 3g is equal to 5a. So 5g minus 3a minus 3g is equal to 5a. So I've got 8a, 5g is 2g, a quarter g. So a is equal to a quarter g. Okay, now I can work out the tension. A quarter of 9.8, by the way, is just 2.45. That's a quarter of 9.8, isn't it? Yeah. Meters per second to the minus 2. So I've got the acceleration now. Now I could work out the tension, just put that back in, but I don't need the tension because that's not what I'm trying to find. Okay. Now, let's look at the second part. So this is why this is a hard one. This is 3 meters above the ground. Okay, when it started. After the system is released from rest, after 1.5 seconds, the string breaks. Okay, so this is accelerating down and that is accelerating up. And after 1.5 seconds, we need to find out, okay, first of all, how far this has travelled up and what speed it's going at. Okay, so the first thing that we can do is we can go v equals u plus at. What is the velocity after 1.5 seconds? Okay, so the velocity, the initial velocity was 0. The acceleration is 2.45, and when we times that by 1.5, we get a velocity of 3.675. 3.675. I don't trust myself. I worked these out before, so I'm just going to check them, because I am tempted. I am prone to making mistakes. Those of you that have been taught by me would know that. 3.675 meters per second to the -1. So this block A reaches a velocity of 3.675. Okay, if we find out how far it travels in that time, we can, what equation of motion has time in it and distance is the S one, isn't it? So S equals ut plus a half a t squared. So let's see how far it's travelled. So S is equal to the initial velocity was 0, so that's useful. A half times the acceleration, which was 2.45, times t squared, 1.5 squared. So 0.5 times 2.45 times 1.5 squared equals 2.75625 meters. Ooh, that's been accurate. Above the ground. Okay, and if we know now that it was already 3 meters above the ground, so after 1.5 seconds it's reached 3 meters and another 2.75625 meters. Okay, so now if we add that to the 3 meters, it is now 5.76 meters above the ground, isn't it? Okay, so let's have a look what's happened and what we do now. Okay, well, we don't need that anymore. Okay, we don't need this working. Okay, what's happened? This block is now here. Okay, it is now, there's the ground, it is now 5.76 meters above the ground, and it is travelling, it's reached a speed of 3.675, but it's not going to be pulled up anymore because there's no force pulling it up. The string has just snapped, so it was accelerating up, and at that point, okay, in time, the string snapped and the velocity is 3.675. So what's going to happen to it now? Well, what's going to happen to it, it's going to slow down under gravity, reach its maximum point, which we're not asked to find this time, and then it's going to hit the ground here. And the question is saying, from the point when the string breaks, how long is this journey? Slowing down and then speeding up and dropping all the way down to here. Okay, so if we take this as our S equals 0, displacement 0, from the starting point, as if this was the start of a question, okay, this point, of course, is the point S equals minus 5.76. So we want the time for it to reach a displacement of minus 7.6, because that's below the 0. Remember, down is going to be negative, up is positive. And if up is positive, it allows us to put the initial velocity in as a positive number, which is 3.675. So 3.675. So I'm going to go 3.68. That's our initial velocity. Okay. Now, we are now going to, let's rub that out. The next stage is we're going to say how long to reach here, and we're going to go S is equal to ut plus a half a t squared. Now straight away we're going to change that because the acceleration, of course, is minus 4.9. That's from our SUVAT ones. Gravity is always minus. Our gravity is always minus 9.8, isn't it? Okay, pulling down the opposite direction. So when we put it into this, we have ut minus 4.9 t squared. That's a half of the acceleration, when of course the acceleration is gravity. That's why I made the mistake saying 4.9 there. Okay, so the S is going to be minus 5.76 in this mock-up of what's happening. We know that the initial velocity is now 3.68 t. We don't know the t. Minus 4.9 t squared. Take everything over to that side and we get 4.9 t squared minus 3.68 t minus 5.76 is equal to 0, and there's your quadratic. Now when we solve that, minus b is minus 3.68, so that is 3.68 plus or minus the square root. Now I'm only going to do plus because I want a positive time, okay? We don't want a negative time, which would take me back in time, which doesn't exist in the real world, down to here. So we want the positive time of b squared, so 3.68 squared, minus 4 times a, 4.9 times minus 5.76, all over 2a, and 2 lots of a is 9.8. So I'm going to put that into my calculator now. Now the way that I'm going to do that is the minus and minus here, all of that is going to be plus. So I'm just going to create my fractions. I don't know if you can see that. Jeff told me that you can't. Okay, so there's my fractions. So 3.68, can you see it here? Plus the square root of 3.68 squared, and I'm going to put plus because it's minus a minus, plus 4 times 4.9 times 5.76, and I'm going to move that out and then down and put it all over 9.8, and when I press equals, that is going to give me the answer. And you can see that it's 1.52 seconds. I was looking at the screen, so I hope I didn't drift off like that. So it's 1.52 seconds, so in 1.5 seconds time to 1 decimal place. Okay, and there we go. It's not going to get harder than that. That's about as hard as you can get, but they do like that one, the string snapping. So it's speeding up. The moment the string snaps, tension's gone, it slows down under gravity and then hits, down. So we could do, like in the example one, find that particular height. We could find that highest point if we wanted to. This question was just concentrating on the time from that point to go there, and we had to do some maths to find the initial velocity, in other words the velocity it had reached, and so on then, and take its deceleration under gravity using S equals ut plus a half at squared. Okay, good. It is hard, that.